Imagine a world where organ shortages are a thing of the past, where life-saving tissues can be printed on demand. This isn't science fiction, it's the groundbreaking field of 3D bioprinting. While this technology holds immense promise for creating human organs and revolutionizing healthcare, it's still a field in its early stages. Significant hurdles remain before widespread clinical application becomes a reality. At its core, 3D bioprinting is an advanced manufacturing process that uses bioinks, mixtures of living cells and biocompatible materials, to create complex biological structures layer by layer. Think of it like a regular 3D printer, but instead of plastic or metal, it's building with the very components of life. The ultimate goal is to fabricate functional tissues and organs that can be used for transplantation, drug testing, and disease modeling. This revolutionary approach aims to replicate the intricate architecture of natural tissues, from the smallest cellular details to the overall organ structure. By precisely depositing cells and biomaterials, scientists are working to create organs that not only look like their natural counterparts, but also function identically. This precision is crucial for ensuring the viability and effectiveness of bioprinted structures. The advancements in 3D bioprinting are truly remarkable, offering solutions to some of medicine's most pressing challenges. From addressing critical organ shortages to revolutionizing drug discovery, its potential impact is vast and far-reaching. Each application represents a step closer to a future where personalized medicine is the norm. A fundamental aim of 3D bioprinting is to replicate the natural cellular microstructure with incredible fidelity. This involves precisely depositing biomaterials and viable cells in specific patterns. The goal is to create organs and tissues that closely resemble their natural counterparts in both structure and function, ensuring they integrate seamlessly into the human body. Achieving this level of biomimicry is essential for the long-term success and functionality of bioprinted constructs. Bioprinting offers a potential solution to the critical global shortage of donor organs, a crisis that leads to countless deaths annually. It envisions a future where organs could be created on demand, tailored specifically to individual patients. This would eliminate the agonizing waitlists and the tragic loss of life due to a lack of suitable donors. Furthermore, it could bypass issues of immune rejection, as organs could potentially be printed using a patient's own cells. Significant progress has been made in developing a range of tissues using 3D bioprinting techniques. Researchers have successfully created heart valves, living heart tissues, and hepatic tissues, paving the way for more complex organ fabrication. Skin, the largest organ, has seen particularly impressive advancements. Large amounts of autologous skin have been manufactured and successfully transplanted in patients with extensive skin defects, offering hope for burn victims and those with severe skin conditions. 3D printing technology has already enabled the creation of incredibly realistic cardiac models that mimic the feel, mechanical properties, and elasticity of actual heart tissue. These lifelike models are proving to be extremely useful for surgical training, allowing aspiring surgeons to practice complex procedures in a risk-free environment. This hands-on experience can significantly improve surgical precision and patient outcomes, reducing the learning curve for intricate operations. One of the most critical breakthroughs involves the development of methods to 3D print intricate vascular networks that closely mimic naturally occurring blood vessels. This marks significant progress toward manufacturing implantable human organs, as a functional blood supply is essential for delivering nutrients and oxygen to cells within any large tissue construct. Without proper vascularization, bioprinted organs cannot survive or function effectively. The ability to 3D print organs means they can be precisely tailored to meet the unique anatomical and physiological requirements of individual patients. This level of customization is a cornerstone of personalized medicine, ensuring that transplanted organs are a perfect fit, both structurally and functionally. Such bespoke organs could lead to better integration, reduced complications, and improved long-term patient health. 3D printed human tissues offer more precise and ethical alternatives for studying drug effects, disease toxicity, and progression. By using human-specific tissues, researchers can gain more accurate insights into how drugs interact with the human body, reducing the need for animal testing. This not only addresses ethical concerns, but also provides more relevant data, potentially accelerating drug discovery and development. Despite the incredible progress, 3D bioprinting faces substantial challenges that must be overcome before it can move from the laboratory to widespread clinical use. These hurdles are complex, often requiring interdisciplinary solutions and significant research investment. Understanding these limitations is crucial for setting realistic expectations about the timeline for this technology's full realization. Replicating the intricate architecture of human tissues remains a monumental challenge. Tissues are composed of multiple cell types, each with specific functions, arranged in precise three-dimensional structures. Mimicking this biological complexity, including the extracellular matrix and various cell-to-cell interactions, requires an unprecedented level of control and understanding of biological processes. Ensuring the survival and functionality of cells after the printing process is a critical hurdle. Cells are delicate and require a suitable microenvironment for growth, proliferation, and differentiation. Replicating these precise conditions in a laboratory setting, especially during and immediately after printing, is incredibly difficult. Maintaining cell viability throughout the entire bioprinting process is paramount for creating functional tissues. Developing suitable biomaterials, often referred to as bioinks, is a major limitation. These materials must support cell growth and differentiation while maintaining the structural integrity of the printed organ. Finding the perfect bioink that closely mimics the natural extracellular matrix, the complex network surrounding cells in tissues, is still a work in progress. The ideal bioink needs to be biocompatible, biodegradable, and mechanically stable. Creating a functional network of blood vessels within the printed organ is perhaps the most critical challenge for larger tissue constructs. Without a robust vascular system, cells deep within the bioprinted tissue cannot receive the necessary nutrients and oxygen, leading to cell death. Developing techniques to rapidly and effectively integrate a capillary network throughout the printed structure is essential for long-term viability. Bioprinting can be a slow process, especially when dealing with complex structures and large numbers of cells. Maintaining cell viability during these extended printing processes is challenging, as cells require a constant supply of nutrients and removal of waste products. Speeding up the printing process while maintaining precision and cell health is a key area of research. Even with personalized bioprinting using a patient's own cells, there's a potential for immune response issues if the biomaterials used are not fully biocompatible with the recipient's body. The body's immune system can still recognize foreign components, leading to rejection. Ensuring complete biocompatibility of all components within the bioprinted construct is vital for successful transplantation. Printing human-scale tissues and organs remains a significant challenge. While small tissue patches have been successfully bioprinted, scaling up to create a full organ, such as a kidney or a heart, introduces immense complexity. The sheer volume of cells, the need for extensive vascularization, and the structural integrity required for a large organ are formidable obstacles. The ethical implications of bioprinting are profound and require careful consideration. Concerns include genetic privacy, the potential for commercialization of human tissues, and the definition of life when creating complex biological constructs. Public discourse and robust regulatory frameworks are needed to navigate these complex moral and societal questions responsibly as the technology advances. Despite the challenges, the future of 3D bioprinting is incredibly promising, with researchers actively pursuing innovative solutions. The field is characterized by rapid advancements and a collaborative spirit, pushing the boundaries of what's possible in regenerative medicine. These future directions offer a glimpse into how bioprinting could transform healthcare in the coming decades. The development of advanced bioinks that more closely mimic the natural extracellular matrix is crucial for future success. Researchers are exploring novel materials that can provide better structural support, promote cell growth and differentiation, and degrade safely within the body. These next-generation bioinks will be key to creating more functional and durable bioprinted tissues. More effective strategies for creating functional vascular networks within bioprinted organs are a top priority. This includes exploring microfluidic channels, sacrificial printing methods, and integrating endothelial cells to spontaneously form blood vessels. Breakthroughs in this area will unlock the ability to print larger, more complex organs that can survive long-term in the body. Combining bioprinting with cutting-edge technologies like machine learning, organoids, and microfluidics could offer new possibilities in constructing functional organs. Machine learning can optimize printing parameters, organoids can provide complex cellular models, and microfluidics can precisely control the cellular environment. This interdisciplinary approach promises to accelerate progress significantly. Advancements in stem cell research provide a promising solution for the future of organ transplants. Using induced pluripotent stem cells, iPSCs, from a patient's own body could eliminate immune rejection entirely. Continued research into stem cell differentiation and maturation will be vital for generating the specific cell types needed for complex organ structures. Extending the culturing period for printed blood vessels and other tissues could allow the cells to fully develop a strong, mature structure. This post-printing maturation phase is critical for ensuring the bioprinted construct achieves full functionality and stability before implantation. Optimizing these culturing conditions is an active area of research. Research is being conducted to accelerate the degradation of hydrogels, which are often used as temporary scaffolds in bioprinting. The aim is for these hydrogels to dissolve within a few months, while the cells mature into functional blood vessels or tissues. This controlled degradation ensures that the natural tissue takes over, leaving behind a fully integrated biological structure. While the bioprinting of complete, functional organs for transplantation is still a long-term goal, significant progress is being made in the field. With continued advancements in technology, dedicated research, and robust collaboration among scientists, engineers, and policymakers, 3D bioprinting holds the immense potential to revolutionize medicine and eliminate organ shortages in the future. The journey of 3D bioprinting is a testament to human ingenuity, but it requires continued support. Learn more about this incredible field, share this information with your community, and advocate for increased funding for biomedical research. Your awareness and engagement can help accelerate the development of life-saving technologies, bringing us closer to a future where no one suffers from organ failure. Hey, if you're enjoying this video and want to see more like it, don't forget to hit subscribe and turn on the notification bell so you never miss an update.